Right, so let us begin with a recap of what we learned in the previous lecture, which is first law and the applications in the basic four type of processes. So the statement of first law of thermodynamics. So here in physics, we will be expressing it slightly differently compared to how you do in chemistry. We'll express it as the net heat supplied to the gas is equal to the change in the gas's internal energy plus the work done by the gas. So the difference here is W is work done by the gas. So Q is the net heat supplied to the gas during a thermodynamic process. Okay. Delta U is the change in internal energy. And W is the work done by the gas. Okay, whereas you will see the alternate way of expressing it in chemistry is like this, that heat supplied plus work done on the gas. So I'll write that as W prime instead of W so that you can understand the difference is equal to the change in internal energy. So here W prime was work done on the gas, not by the gas. So obviously work done on the gas is negative of work done by the gas. Hence, we can also express it in this way like we do in physics. So here W, work done by the gas, is integration of Pd. It is such that during an expansion, W is positive, whereas during compression of the gas, the work done by the gas is negative. Whereas W prime is defined as minus of integration Pd, the work done on the gas. So that will be a negative quantity for expansion. Because if the gas expands, the work done on the gas is negative. dV is positive, so W prime is negative. Whereas if the gas is compressed, then the work done on the gas during that process will become a positive quantity. It's just opposite of this equation of work done by the gas. So this is work done is a path function. Whereas delta U is this much. So delta U is a state function, or internal energy is a state function. From kinetic theory of gases, we have seen that internal energy is the total kinetic energy of gas molecules. So this concept from kinetic theory of gases translates to the formula of delta U for first law of thermodynamics. and Q, which becomes the sum of delta U plus W. This also becomes a path function because W is a path function. So Q also has to be a path function. So hope this is clear to all of you. Please ask me if there's any doubt. Okay, then the next thing we had seen was the application of this first law of thermodynamics for the four standard processes. So we'll quickly go through that once more. So isobaric process, volume is constant or dV is 0. So work done becomes 0. So Q is equal to delta U. Okay. So it is always like this because there is a state function. So therefore Q equal to NCV delta T is equal to delta U here. So therefore CV is equal to F by 2R. This becomes an important formula. Okay, next up, we've seen the second type of standard process, which was the isobaric process. So I'm just doing a quick recap of these things because you already know these from chemistry. So isobaric means pressure is constant. Okay, or change in pressure is zero. So pressure is constant means work done, which is integration PdV, becomes P delta V, and secondly because PV is equal to nRT, so P delta V is nR delta T when pressure is constant. Okay. So work done, which is P delta V, can also be defined as nR delta T. So this is the path function. Okay, then the state function delta U is the same formula. So Q being delta U plus W, Q becomes this plus this. Okay. So you can express Q in this way, which is NCP delta T. So from here we also get the formula that Cp is F by 2 plus 1 R, or that Cp is equal to Cv plus R. So there's another important formula here. So Cp is equal to 5 by 2 R for monoatomic gases, and becomes 7 by 2 R for diatomic gases. Okay, then the next type of process, the isothermal process, where temperature is constant, so pressure is inversely proportional to volume, or this comes from the ideal gas equation. So work done which is integration of PdV becomes okay. Varun, you can just go through this section. It's there in the previous lecture notes, so you don't need to write down in detail. Just go through this and make sure you understand each thing. The rest of plus you've done this in chemistry also, so this is just a recap of the concept. Okay. Now temperature is constant, so delta U becomes 0 because temperature T is constant. Or so Q becomes equal to W, becomes equal to nRT natural log of final by initial volume. Okay, so before we proceed further, let's look at an example problem with the application of these. So pressure versus volume graph is given to us for a gas. Now, Okay, just quickly work out this question, people. We'll discuss. So anybody got the answer for this? Okay, so let's work out quickly. So AV is isothermal process. Okay. So temperature is constant. So temperature at B is equal to temperature at A, which is 300 Kelvin. 300 Kelvin. So this isotherm is for 300 Kelvin. So temperature at A is equal to temperature at B. Okay. And product of pressure into volume is constant. So therefore pressure at B will become 0.5 atmospheres. Then B to C you can see is isobaric compression. This was an isothermal expansion. So pressure is constant. So from that we can see that volume is proportional to temperature. So temperature at C becomes 75 Kelvin. Now the second thing, so for the process AB, which is isothermal expansion. So Q is equal to W is equal to nRT natural log of final by initial volume, and delta U is 0. So that is converting liter atmosphere to this SI unit. So 1 liter atmosphere is 101 joules, or you can also approximate it as 100 joules. So this becomes for the process AB. Also ln4 we can write as 2 times ln2. So that is so now similarly you work it out for BC, which is an isobaric compression. Calculate the value of Q, delta U, and W. Yeah, Rahil, see, this is how we have got 202 joules. 1 liter atmosphere is 100 joules or 101 joules, or we can approximate that as 100 joules. So this is how we get that. Understood better? 1 liter is 10 raised by minus 3 meter cube, or 1,000th of a meter cube, and 1 atmosphere is 1.01 into 10 raised by 5 pascals. So 1 liter into atmosphere becomes this. In SI unit, in terms of meter cube into pascals, this is meter cubes into pascal. So meter cube into pascal is 1 joule. So this becomes 101 joules. So this is clear, Vidam?
Yes, sir.
Okay. Okay, now similarly we have to do the calculation for the second part, which is the isobaric compression, B to C, as you can see. But in this, remember that the gas undergoing the process is nitrogen. So nitrogen is a diatomic gas. So degrees of freedom is 5. So Cp's value will be 7 by 2R. So this we have to apply over here. So for BC, you can see isobaric. So Q will be NCP delta T. W will be NR delta T or P delta V. Just a moment, I'll share the file again. Okay. So isobaric process में we use the formula Q is NCP delta T. W is NR delta T or P delta V, and delta U is NF by 2R delta T or NCV delta T. Okay. So you can see temperature at C was 75 Kelvin, and this pressure is 0.5 atmospheres. Okay. We can write this way. So this term becomes the pressure of zero point 0.5 atmospheres into this in liter atmosphere. So minus 1.5 liter atmosphere. That is in joules. Okay. So this term Q becomes 7 by 2 into this. Similarly, delta U and work done Okay, so all this because it is an isobaric process. So these are the formulae we use for isobaric process. Okay, so hope this is clear to all of you. Just make a note of this. Make sure you understand this. Then we'll move on to the next part, which is adiabatic process, then polytropic processes.
तो सर 10 बज गए और जागो 1-1 बजे तक I remember I had
Okay, students, so hope this question is fully clear. Now let's resume the part ahead. So the fourth and final type of standard process, as you know, is the adiabatic process. So adiabatic process is defined as one in which the heat exchanged is zero. Okay. So delta U plus W is zero. Okay, so W is negative of delta U. Now delta U for any process is given by the standard formula. This is a state function. It has the same formula everywhere. So W here becomes this much. Okay. So these are the three standard quantities: Q, delta U, and W. Okay. And also we saw that if we write in differential form, delta Q plus W is zero, we'll get this. So NF by 2R dt plus PdV is zero. And PV equal to nRT. If we write this in differential equation form, we have PdV plus VdP is equal to nR dt. Okay. So solving these two equations, you can see that we'll get this kind of relation. So we'll get this kind of relation, or this, okay, where gamma is equal to 1 plus 2 by F, or Cp by Cv. This is called the adiabatic constant. So we integrate this relation now. We got this relation that or in general PV to the power gamma is constant for an adiabatic process. Okay, where gamma is Cp by Cv, so this is the relation between pressure and volume in an adiabatic process. Okay, so let's do a quick question based on this. Now, before that, the value of gamma, which is Cp by Cv or 1 plus 2 by F. Because remember, Cp is 1 plus F by 2 R and Cv is F by 2 R, or Cp is equal to Cv plus R, all these relations. Okay, so gamma becomes 5 by 3 for monoatomic gases. So these are values you should be absolutely thorough about, so that you can do questions fast without too much back calculation. And 7 by 5 for diatomic gases. And also one more thing you can see is that Cv, which is F by 2R, can also be written as R upon gamma minus 1. And Cp, which is this much, can also be written as gamma upon gamma minus 1 into R. Okay. So these are two additional calculations or relations which are useful to remember. Okay, so let's look at a example question based on adiabatic process. A sample of helium at an initial pressure of let's say 0.5 atmospheres, volume of 1 liter, and temperature of 100 Kelvin is compressed. So let's take the initial volume as 4 liters, is compressed adiabatically to a volume of 0.5 liters. Okay. Obviously, Q is 0 for the adiabatic process. So just try out this question quickly. Use the formula which you can see above we have written down for adiabatic processes. So finish this question quickly, people. Then we'll look at the general polytropic process and heat engines to finish up this section of first law of thermodynamics. Yeah, so anybody got the answer for this? So you'll have to use the equation PV to the power gamma is constant. Okay, now it's helium gas, so it's monoatomic. So degrees of freedom are 3 and gamma is 5 by 3. So pressure at the second point will become P1 into V1 by V2 to the power gamma. Yes, Siddhi, very good. That is correct. Okay. So 0.5 atmospheres multiplied by volume का ratio कितना है? V1 by V2 is 4 upon 0.5 or 8 to the power 5 by 3. So 0.5 into 8 to the power 5 by 3. Now 8 can be written as 2 cube. So that will become 0.5 into 2 to the power 5. So that's 0.5 into 32 or 16 atmospheres. So very good, that's correct. So the pressure is 16 atmosphere. Okay. And for temperature, we can use the relation P1 V1 by T1 is equal to excuse me, this. Okay. So you can see that. Okay. So this value of pressure goes here in this equation, and that's how we. Or you can also use the relation that PV to the power gamma is constant. Also implies that okay, so temperature into volume to the power gamma minus 1 is constant. So T1 V1 to the power 2 by 3 will be equal to T2 V2 to the power 2 by 3 in this case because gamma is 5 by 3. Okay. That's the first part. Now second part, delta U and W. So delta U is NF by 2R delta T. So that is 3 by 2 into P2 V2 minus P1 V1. So 16 atmosphere into 0.5 liter minus initial pressure was zero point 0.5 atmosphere and the volume was 4 liters. So into 101 to convert it to joules. Okay, so the internal energy is increasing by this much. So W will be equal to minus delta U. So work done will be because Q is 0. So this type of direct formula based problem solving is very important for you in thermodynamics, both from chemistry point of view as well as from physics. Yeah, Varun, you can see the value of temperature we've got now, 400 Kelvin. This is how we evaluate the temperature T2. Yes, Varun, this is clear now, beta?
Yes, sir.
Calculation of temperature. Yeah?
Yes.
Okay. Okay, so this is about adiabatic processes. Now, let's move on to the next part, cyclic process and later polytropic process. So by cyclic process, we mean a process such that the gas exchanges heat and mechanical work. Okay. And returns to the initial state. So whenever this happens, we call it a cyclic process. So as the name suggests, the term cyclic process comes from the fact that the PV graph, the gas will look like a closed cycle. It will look like a closed loop. So the general sort of graph, whatever be the process it is undergoing, if it starts from the point A and it eventually comes back, so initial state equals to the final state, which in the graph is A. So that is pressure at A, volume at A, temperature at A, whatever that is the initial state, which is the same as the final state. So this is the PV graph for a cyclic process is a closed loop always. Okay. So the first important property of a cyclic process is that delta U for a cycle will be zero because U is a state function. So if initial state equals to final state, that means initial internal energy equals to final internal energy. So delta U must be zero. Okay. So therefore, Q for a cycle is equal to W for a cycle. That is the net heat given to the gas is equal to the net work done by the gas during the cycle. Okay, now the next thing is that the work done in the cycle can be calculated from the area enclosed within the closed loop of the PV graph. Okay, so let's understand how this happens. And there are two cases over here. Okay. So case one is the clockwise PV cycle. If the PV graph looks like a clockwise cycle, then how to calculate the net work done? For example, if this is our PV graph, so as you can see, the cycle is looking clockwise. And this is clockwise. Okay. So now let's just consider the initial state as the final state. That one is the point A. Okay. So if we consider another point B over here, then you can see is equal to the work done from A to B plus the work done from B to A. Now work done from A to B will be positive of this larger area, because A to B is this process, should be this area. This area is, let's say, A1. So it is positive of A1 because there's an expansion happening. Okay. Whereas now if you consider the work done from B to A, that will be this smaller area, just this much. So net work done in the cycle so that is positive of the area enclosed by the loop. So in the case where it is a clockwise cycle, the work done during the cycle becomes positive of area enclosed by the loop. Okay. Just make sure you understood this point and discuss with me if you have any doubt about why it is positive of the area. Okay. And next we will discuss the anti-clockwise cycle, and there you will see the logic is opposite of this. Okay, so now let's see the second case, which is the case of an anti-clockwise cycle. So if we have a PV cycle, which now let's say looks like this, it's an anti-clockwise loop or counterclockwise. Okay. Now let's say again this is the starting point A. So initial equal to final state A. So if it goes from A to B somewhere here, let's say first, then A to B the work done will be positive of this area. This area is A1. So work done from A to B will be positive of A1. Okay. But then in coming back from B to C, sorry, coming back from B to A, the work done will be this total area, but with a negative sign. So it's a compression. This was an expansion, so the work done was positive. But work done from B to A will be negative of the area A2 because it is a compression. So now you can see that work done in the cycle ABA, that is work done from A to B plus work done from B to A, algebraic sum. So it is plus A1 minus A2. So it becomes negative of the area enclosed by the loop. Okay. So this is what happens in the case of an anti-clockwise cycle. So it's very important you understand this next because we are going to discuss about heat engines also after polytropic processes. So heat engine cycles are the type of cycles where the work done is actually positive. So it's the clockwise cycles. Whereas anti-clockwise cycles where the net work done is negative, they are what we'll see is reverse heat engine cycles or refrigeration cycles. We must have done heat engines in chemistry also, including Carnot cycle, etc. So we'll be discussing those things. Yeah, Sarvesh shall explain it. So see, Sarvesh, what is happening here is in this cycle, we are first going from A to B via this path. तो ये वाले पाथ में क्या हो रहा है? एक्सपेंशन हो रहा है, वॉल्यूम इज इंक्रीजिंग. So this area, so work done A to B is integration P dV. So this area is A1, it is positive of this area A1. This point is clear, Sarvesh?
Yes.
Okay. Now next what is happening now? We are coming back from B to A, but via this kind of process. Okay, just a moment. Yeah. So the second thing now, when we are coming back by this kind of process. This, okay. So this is a compression, you can see. So during the compression, it's this area, but with a negative sign. This area is A2. So the work done from B to A is negative of A2. This clear, Sarvesh?
So, but area is not negative.
क्या हो गया?
So, why area is negative?
Why area is negative ना? Because integration P dV करोगे आप तो उसमें dV कैसा क्वांटिटी है? नेगेटिव है ना? Work done is integration P dV. So for a compression, okay, dV कैसा क्वांटिटी है? नेगेटिव है ना? So work done कैसा हो जाएगा? नेगेटिव. For example, if we take an isobaric compression, okay, now isobaric compression कैसा दिखता है? ऐसा दिखता है. Pressure is constant. Okay, let's say pressure is P naught. So suppose we have P naught equal to 2 atmospheres and V1 equal to 2 liters and V2 equal to 3 liters. So यहाँ पे work done क्या हो जाएगा? P delta V. So that is 2 atmospheres, but into 2 minus 3 liters, na? Because we are going from this point to this point. So it will be, as you can see, it will be minus 2 liter atmosphere. So anytime we are having a compression, the work done has to be a negative quantity. That's why here it is negative of the area. The point clear hai na beta?
Yes.
Okay. So now you can see that this is the work done from B to A. Okay. So now the net work done is the sum of these two, na? Is this
Yes.
cycle में. So ये कितना हो जा रहा है actually? It is minus of A2 minus A1. So A2 minus A1 ही तो ये वाला एरिया है जो enclosed वाला है, ये वाला एरिया जो साइकिल में enclosed एरिया है वो कितना है? उसका मैग्नीट्यूड A2 minus A1 है, तो ये माइनस ऑफ दैट है ना. So that is why it is negative of the area enclosed by the loop.
Okay.
ठीक है. Whereas in this case it is positive, because this case में when I do A1 minus A2, then I get this, no? This area here,
Yes.
this cycle, this A1 minus A2. It's positive of A1 minus A2. ठीक है. So hope this is clear. Okay. So clockwise cycle, Q is equal to delta U is equal to positive quantity. So that means net heat, sorry, Q is equal to W is equal to. So net heat supplied to the gas equals to work done by the gas. Okay, why net heat is supplied to the gas? Because Q is positive. And why work is done by the gas? Because W is positive. Okay. Whereas anti-clockwise cycle, so heat is converted to work. So in a clockwise cycle, you can see that heat supplied is converted to work. So that is why this type of cycle, therefore, this is a heat engine cycle because it converts heat energy into mechanical work. So that type of a cyclic process or that type of a cycle is called a heat engine. Whereas if we look at anti-clockwise cycle, then Q is equal to W is equal to a negative quantity. That means heat is extracted from the gas because Q is negative, and it means work is done on the gas instead of by the gas because W is negative. So it is a situation where work done on the gas is converted into heat extracted. Okay. So उसका मतलब ये क्या हो गया? This is therefore what we call a reverse heat engine cycle. Or it is also called a refrigeration cycle. Okay. So work is done on the system to extract heat or to absorb heat from it. So that's a refrigeration cycle. Whereas if heat is supplied to a system to get it to do work or to get the heat to convert into mechanical work, then it is called a heat engine cycle. Okay, people. So hope the two type of cyclic processes are clear. So we'll conclude today at this point, and next lecture we will look at heat engines in more detail and understand the concept of efficiency. Also do numerical problems related to this cyclic process. Then polytropic process, and with that we will complete first law of thermodynamics and applications. Then we'll be ready to move on to heat transfer from there. This is the last section of heat and thermodynamics. So that's it for today's session, people. Wish you all the best.
Bye, sir. Thank you, sir.
Okay, people, all the best.
Thank you, sir. Bye, sir.